Good evening, mathematicians and lay math enthusiasts. My name is Jeff Cook, and I am here to present the sixth video in this series, a direct proof of the Riemann hypothesis. And if you haven't guessed by listening to the last few videos, I have a new audio system. Actually, I finally broke down, bought a mic and a little mixing board. I couldn't bear to listen to videos, and I'm surprised I even had any listeners to them in the first place. I am not a YouTuber, so I didn't really want to do it and buy a mic, but I figured, well, there are people watching these videos, and even my co-authors are, I can't hear you, and I don't want to hear you. And I'm like, that's not going to work then. So I wasn't going to do it because we didn't make these videos to be YouTubers. We made them just so we could reference to other mathematicians who had questions, so I didn't need to explain the paper over and over and over again to multiple mathematicians. But we have almost 5,000 reads of the paper as of today, and I still have people, even though I very rarely ever make a video, I still have people subscribing, and I feel bad. Thank you. No, I feel good. I appreciate it, but I feel bad because of the very poor audio quality in the past videos. This one may not be better. I don't know. This is the first one I've made with this setup, and I'm really, it's the first time I've done it, so I don't know how to use it. But I'm going to get into things pretty quickly. This video is a very important video. It's going to have kind of three parts, okay? So the first part is answering questions that some of you have had, some mathematicians have had, and some of them quite good. And then there's some counter arguments that have been presented to the paper, and this video is going to describe how we respond to them, so that if you're coming to this if you're coming to this channel, you're watching this video, and you haven't seen the other videos, you're going to have a full understanding of the paper. Because the third part of this, I'm going to give the summary based on some revisions we did, only on some of the wording. We're going to go over that to help make things clear, so that no one has any questions. The paper is like 9 pages long. I think with appendices in the older version, which we've taken out. I'll get into that. Very, very short proof. It's a direct proof of the Riemann hypothesis. If you haven't watched the other videos and you haven't read the paper, I understand your suspicions. So I would have them too, and it is right that you do have them. Okay, but we are all seeking truth, I hope, and therefore, since math is the only thing that is certain, according to Descartes, we're going to really simplify everything that's in the paper. It's already rather simple, but I'm going to go over it with the revisions. So we went over it in the fourth video, how to prove the Riemann hypothesis in less than 10 steps. This actually kind of shortens it down to 3 lemmas and a proof. So it's the same thing. We just organized the paper in the same way. It's in the same order. Nothing's been changed that way. But it's we're given some names. All right, so we're calling this section lemma. This one, we're giving this a property name. Okay, it'll all make sense. So sit back. This is going to be a kind of long video because we got 3 parts. We got questions, counter arguments, little background on the form of the zeta function that is used in the paper, and then the third brief summary. So let's get into it. All right. You're going to need the paper with the latest revisions. You can go to your favorite search engine, type in Jeff Cook Riemann hypothesis, okay? My co-authors are all signed up on ResearchGate now. Finally got Greg to join. He was very impressed with it. I think he's liking it a lot. I'm the second on. Denny's been on there quite some time. All right, so you can go there. I'm not sure how much, if you're not a member, how much you can see of our experience, our other papers. But this paper here, or this preprint paper, is public. So you can do a Google search on it, or DuckDuckGo, or any search. It should be the first one that comes up. So you go and you click on ResearchGate PDF, a direct proof of the Riemann hypothesis. Got it? Good. All right, so this is part 6 of series. I probably will leave a part 7 out in limbo in case somebody finds an error. Right? So I gotta make a video. Somebody makes an error and say, hey, look, it's all over. This is a problem. Or if some mathematicians accept it and defend it, that needs to be another video. I'm probably not going to make any more videos on this from here on out. This should sum everything up. So all the other videos, well, you're going to have to probably go back on some of the explanations on the history of the Riemann hypothesis. If you're not familiar with the Riemann hypothesis, if you're not familiar with the zeta function, yeah, you're going to have to go back to video 1 and video 2 probably as well. So this one should sum up everything about the paper, though, and with the revisions that went in. And you'll see they're not major, but they're clearer, and we've been able to reduce a couple equations. So this should help a lot. Good. Okay, this is there's been a number of questions, but there's 3 that kind of come up a lot. Okay, question 1, and this is have you tried to, actually this one doesn't come up a lot, actually this came up only one time, but it's kind of important because it can sum up all the rest of the other questions. Okay, if I understand this correctly, all non-trivial zeros are of type 1. So if you don't understand what I mean by type 1, you read the paper, you can get into it, and we'll get into it later. But this is the answer of the questions up to date. Okay, all non-trivial zeros are type 1. They are also zeros of upsilon. Is this true? Yes, it is true. Did you try to plug in one of the known zeros into upsilon? Yes, of course. This is very important and very easy to do. In fact, this little way I'm going to show you here shows how you can do it for all of the known zeros having a real part 1/2 and why upsilon, what the value is for upsilon, but also showing that it's 0 and why it has to be 0 when the real part equals 1/2. Now, there are 2 types where upsilon not be equal to 0, which we'll get into. There are zeros of the zeta function that has upsilon not equal to 0. But all of those having real part 1/2 will be equal to 0. All right, so here's how you do it. The answer is yes. And so here's upsilon in its rational relationship to the zeta function. Okay, so if we consider first, since we could work with the innermost parentheses. Okay, so there's no powers there, so in order operations we'd have to do powers first. But since this is the innermost parentheses, we can do this. We're just going to let it equal a critical 0. All right, and it goes to 0, of course, right? So it's a critical 0 on the real part, on the having a real part 1/2 on a critical line. We're going to reduce that, and it becomes this quadratic. Okay, so yes, you can expand it. I was going to put it in the video, but just lack of time didn't do it. But yes, you can express this as a quadratic. What's left over when zeta goes to 0 is purely a rational quadratic form of upsilon. Okay, so there's that. Now, if we take this and forget that we're talking about, take the rest of the s's, okay? All those s's remaining there, watch this, and we're going to just kind of call it 1 over x. Forget that we're talking about 1/2, all right? We reduced it for a critical 0, but I want you to see why it goes to 0, and for everyone. And mathematicians would get it, but I want everyone to see. All right, so what happens when we do this, all right? And we kind of express it in terms of 1 over x. If that reduces, okay, this reduces all to this, all right? Look at the numerator. What happens when x becomes 2? If the real part is 1/2, 2 minus 2 is 0. It wipes out the entire numerator. You see that? So anytime that happens, you have a real part 1/2 and the zeta function equals 0, upsilon is going to equal 0, okay? So that's what happens. And that's how you can apply it. But you can also apply it individually and give it an imaginary part. Here we just kind of do generic imaginary part of non-trivial 0. Okay, so that was question 1. The individual who asked that, anyone else that would ask that is going to get that. All right, let's do something more general. Question 2, why don't you upload this to archive? Well, quite frankly, as I just said, and I've told other people, we prefer researchgate.net. Has a nice community. Everyone's public there. I can see all the information about other researchers. They can see it all about me. So pretty much because of that, everyone's nice. And I like that. Yeah, everyone's very polite. They may politely be silent, but they're super nice. Those who do communicate with me, and it's just a great community. It's social media for researchers. So why would I go to archive? You can have your papers there, whether you're published or not, in preprint or not. Archive, as I went and looked into it, it's kind of like it says, please do not upload anything unless you plan on publishing to this journal. And I'm like, I don't want those kind of restrictions. I don't want any restrictions. I just want to upload it. All right, I'm a published researcher. I should be able to upload anything I want. So there's a number of reasons why I don't see the need for it. I don't really like centralization in the first place. So I have no interest in archive. Now, if Greg and Denny go, they can upload the paper. That's fine. But to my understanding, they don't have any interest either. So I don't have a problem with archive. I just prefer ResearchGate. That's all. Okay, question 3. This was a big one. And this was asked by I don't know about, like, how do we say this? Those at the higher level of certain universities and mathematics have even asked this question. How do you solve it? They didn't ask how you solve it. They just said, how did you get that? Or something like that. And I'm like, well, I can show you the solution, derivation. They're like, yeah, that'd be good. Okay. So then I realized, okay, so then it's not that easy. I thought it was, and software applications can do it. Wolfram Alpha can do it. But yeah, so I figured, let's do this. Let's reduce this. And that mathematician asked, super nice about it, gave us a reduction. And so we put it in there. He wishes not to be named. I hope only at this time. So the answer is basically we did upload those solutions to ResearchGate, and then we put them in the appendix, and then I just took it out. Once we have a reduction of 7/8, there's no reason we need to do that anymore. We don't need to have any attachments or anything. The paper is clear. All right, just wrapping up a few of the questions from earlier. Okay, so the appendices are gone. There's no reason for it. The paper is super clear now. It already was, but like to add as much as we can to make sure. But sometimes explaining things too much is just taking things into darker corners, which is kind of what I'm doing right now. So I'm gonna keep on moving. Counterargument 1. Now you're gonna read these and say these aren't really counterarguments, but this is the best we're getting. We have not had anyone find errors, and we got a lot of talk on it, but no errors. Okay, this is really good if you're on our side. But if you're you're not wanting the Riemann hypothesis to be proved by us, it may not be good. So please prepare a counterargument. We are interested in them. All right. And as you see right here, I'm going to present them. And I think I sum up all of the counterarguments we've had in these 3. Okay, because I kind of wrap them all into 3 things. But let's just take one general type of counterargument that's been coming our way is something like this. This is one example. This is an actual comment, but it kind of goes along the lines of some of the others. It's not a counterargument. Just watch. All right. Per this sentence, this was in the abstract. All right, or before it's been revised. All right. A function upsilon of s is derived that shares all the non-trivial zeros of the Riemann zeta function, but none of the trivial. And the comment, I don't know if it was a counterargument, it was this. You will not get anyone to take your proof seriously unless you can show that upsilon of s is the completed zeta function. This would be one of those things you'd want to think about. All right. What does that have to do with upsilon in the first place? But let's kind of go deal with it. What is he talking about? What is the completed zeta function? Well, it's this super tricky, amazing, unbelievable mathematical miracle having to do with the argument in the gamma function where you multiply it by -1. Okay, it's a really sophisticated maneuver there. All right, and by doing that, you undefine all of the trivial zeros. Okay, and why would anyone want to do that? All right, so in our proof, we're not intentionally trying to make upsilon of s not be a 0 when the trivial zeros are applied. It just so happens to be that. In this case, for what's called the completed zeta function, I think there's a total of like 1.5 papers in all of the literature written on this. They want to kind of isolate a function so they can say all the zeros in the critical strip are here in this function, and they do that by undefining the trivial. So this is how bad this is. First of all, that's wrong. All right, the comment is bad. The situation is not. So any attempt to find the Riemann hypothesis, I don't care how silly it looks or how rudimentary or how complicated. If you're trying to solve something, throw everything at it. Okay, so this is really useful. I don't know if it actually led anyone anywhere. All right, but we're not talking about the completed zeta function. We're talking about upsilon. It's not even a zeta function. I don't know how you would even call it that. So upsilon doesn't equal the completed zeta function. So why would anyone expect it to be that? It makes no sense. And so I forgot to take that out. No, I'm just kidding. So look here. here's what we'll be doing. All right, so I'm gonna do something about that. All right, so since this was in the abstract and we had this sentence here, we don't want anyone to stop anywhere in the paper and go, well, no. We want to keep it moving all the way to the end. So to fix this situation, we're just going to remove that, but none of the trivial. A function upsilon of s is derived that shares all the non-trivial zeros of Riemann's zeta function. That's it. That's all we need to talk about. I don't need to discuss it. And we don't need to discuss with that mathematician anymore. Okay, so I'm going to rate that counterargument 1 star. Okay, the next one is, this one comes up, this is not from, and that, oh, by the way, that mathematician has his PhD, so he's not a, lower rung mathematician. He's one that is fairly accomplished. All right, not a household name, but okay. So not even in the field of mathematics, but he's a nice guy. All right, it's just that I don't understand that. All right, here's the thing. Okay, so this was in there before. All right, and we had stated given a plus b plus c equals 0, there are only 2 types of solutions. Why did we have that? All right, so. This was not a consensus. This was between me and my co-authors. This was mine because people were not getting the other one. All right. And so I'm like, look, guys, this is simple. Let's reduce it down to elementary. And I just left it in the paper. But then people are getting stuck at this one too. They're like, no, there could be 3 solutions. It could be 0 plus 0 plus 0 equals 0. Okay, well, great. That's more of an identity in the solution, but and anything times 0 is going to equal that. I could probably bring that into the type 2 solution, but let's just kind of see what steps we've done in the revisions to fix that. I just eliminated it again. It wasn't there in the beginning. It's not there anymore. And you see I kind of just put this is the form we're describing right here. And then I simply say down here, this statement will be proven. All right, it says, in the top one, with A, B, and C having no roots, there are only 2 types of solutions. And I give the identity or expression. No, so what is this? This is a solution. Yes, for 0. Good. And we just say, and so no one stops reading the paper here. We say this statement will be proven in the case of the Riemann zeta function. I don't need to say it's any function has it. I don't care to prove it. We're only proving it in terms of the zeta function. Good enough? Good. All right. We're going to rate that with 2 stars. And the reason I give it 2 stars is because my wife was one of those. Actually, because of my wife, I better give her 4 stars. But those 4 stars are only for her, okay? And she's not a mathematician, so she gets extra for that. Good. Okay. Counterargument 3. This one is pretty significant. I'm just going to read it to you, and because this is the one. This is the issue that is keeping papers, not this one necessarily, but papers in general, out of journals, all right? This is a big issue, and it needs to be remedied, and it doesn't have to do with our paper. Here we go. You derive upsilon from Riemann's functional equation, and this is kind of a paraphrase of a lot of different comments on this. All right, but Selberg Euler products have functional equations similar to the zeta function. They share all the same analytic properties, have Riemann's symmetric vertices property, and have zeros off the critical line. Therefore, your proof must be incorrect. No, not necessarily. All right, you have to first take a Selberg Euler product and apply it to this proof. And if you do, you will see that it won't apply because this is not an analytic proof. Therefore, it doesn't matter if Selberg Euler products share the same analytic properties as the Riemann zeta function. Let's show you what we do about this. All right. Before I even get onto this, look, there are journals right now, as we speak. We're getting papers, and if the functional equation, Riemann's functional equation, and I have it somewhere around here, appears on the proof, they toss it aside. End of story. As long as that functional equation is in there, they will set it in the slush pile. And this is incorrect, it's irresponsible, and it is not an accurate understanding of Selberg Euler products, okay? So if you have the functional equation in there, then you take a Selberg Euler product and you apply it to the proof in question and it passes, then yes. Then you say, okay, well then the proof is wrong because we just applied the function, our Selberg Euler product, which I'm going to explain here, and to the proof, and it survives also, but it does have critical zeros off the critical line, or non-trivial zeros off the critical line. Okay, so that would be a big problem. And this is what mathematicians who understand the problem will do. They'll take the Selberg Euler product, apply it to a proof that has the Riemann's functional equation in it. But we can't really go along with the saying, oh, because they share all the analytic properties, that there's any similarity necessarily because of, as I'm going to show you. Because here's the big reason. Riemann's final result, all right, so on a number of primes up to a given magnitude or less than a given magnitude, is that equation is not an analytic function in itself. The Riemann hypothesis is not an analytic problem. Yes, he used analysis, but up to a certain point, and then the function ceases to be analytic. All right, so we're using an algebraic proof, and this is kind of goes hand in hand. And mathematicians say, well, there's simply no way you could have an algebraic proof of the Riemann hypothesis without anyone else finding it already. I beg to differ. As you go through this video, you will see, yes, this is a pretty novel attempt, and it's very clear. Okay, watch carefully. So we put a little discussion about Selberg Euler products. All right, so here's one. I just kind of put it in there. This is the general form. Okay, so the Selberg products probably do not have L functions, and if they do, they're not going to be in the same form as the Riemann zeta function. There's got to be some property of Selberg Euler products that is different than Euler products or non-Selberg, let's say, that like the zeta function would be a non-Selberg Euler products. So what is a Selberg Euler product? Well, you can do a simple one here, as I did. Now, Greg, my co-author, was saying, well, shouldn't we do a simpler one if we're setting an example? I'm like, well, it is the simplest in that it has a trivial zero that's going to come from this. It has critical zeros, those having real part 1/2. It's going to have some off the critical line. Okay, so that would give us Selberg Euler product with this in the simplest form that it has critical zeros, non-critical, non-trivial zeros, and at least one trivial zero. Okay, so here's the big issue. Look at this term. This function here. This is a different form. It's not an infinite series, obviously. It's not an infinite Euler product, but it's a good example. All right, look. Which one of these terms can equal 0? Even if we reduce this to kind of bunched together, combined, terms together, which one of them is going to equal 0? The only one would be s equals 0, but since that's not a 0 of any of the Euler products that wouldn't be valid. So none of them can equal 0. Well, then it's going to fail as a type 2 0. It doesn't have the new property, which is, we're giving it a name, the mutual exclusive property. All right, and we're going to talk about it a little bit. Before we said there's two types, okay, and there's type 1, which is when upsilon equals 0, so zeta equals 0, and upsilon equals 0. It's going to have this. It's going to be equal a equals minus c times omega squared. The type 2, that's a linear. It's going to all be in a straight line. And in this case, they're all on the critical line. So all type 1 have real part 1/2. Type 2 are planar. They're going to exist as on the corners of vertices. Whether or not they're symmetric across the critical line or the real line is to be determined later. Okay, those are type 2. That's upsilon not equal to 0. Okay, so it doesn't reduce. It's the same thing if you want to see my cursor. Good. All right, so at least one of the terms in the zeta function must equal 0 for it to be a type 2, because the type 2 is that one term equals 0 and the other two negate each other. That's type 1. The other type 2, is that two terms negate the third, all right? Or a certain number negate all the others. But one of them has to go 0, and that would be with upsilon in this case, and all of them have to have one term that goes to 0. And otherwise, you're not even be able to get through the proof. It doesn't make sense because you're not even dealing with linear solution. So I have applied a number of Selberg Euler products to this proof. None of them, they don't get past the first lemma. Okay, they don't get past the first lemma. And I had a mathematician looking over it, and he's going, I think it's impossible. You're doing it. No, you're trying it with the Euler, the Selberg Euler product. It's impossible with them. Do it with the zeta function. It works nicely, and then that sums it up. Okay, for this counter argument, I'm going to give it no stars for you. Okay, I'll give you 4 because this is going to make the proof stronger. It is going to make the proof stronger by adding some discussion. That way, when they see the functional equation, we start off right at the bat and say, well, this is going to be different. In fact, it's very powerful because we can test whether or not you are applying a Selberg weather product or a non-Selberg. This proof will also work to do that. And that's kind of neat because it also shows what is the difference between the two. To date, it's not known. Here it is known. And it comes right there with the mutual exclusive property, which was already in there, but we just gave it a name, okay? And we kind of refine it. All right, so now we're going to get into this summary. And like I said, it's this, that was just some of the questions and counter arguments. So the really good stuff is getting started now. That was a little background for those who watched the other videos. If you're new to this proof and you haven't read this paper, these next parts is going to be very important, all right? And if you have watched the other videos and you're familiar, but you're going to want to watch it for some of the revisions. They're minor, just like the Selberg other products, but let's kind of go through. All right, this is a direct proof. All right, what is a direct proof? Well, we're going to start with a premise, something that is true or something we're going to prove to be true, and then we're going to build off of it. So it may have something that depends on that premise, will also have to be proved as well. Now, let's suppose we have P2 may depend on, I don't know, commutativity of addition, but it's also going to be dependent on P1. Maybe P1 is new, all right? So we're going to create some premises, and we're going to go a straight line, prove one, and then the next, and then the next, all the way to the proof, okay? That's a direct proof. So we don't have to do any proof by contradiction. We don't need to go back and do something. For example, a direct proof would be most algebraic manipulations are direct proofs. So, for instance, somebody asked and think, why did you say that, what was it? I'm trying to remember what it was. It was something, you know, something equation implies such and such. And I'm like, oh, well, you just do this, multiply by 2, add 1, and there you have, you know, that. So it goes step by step by step. So those of you who aren't familiar with direct proof, that's what it is. So other proofs, there's many types. There's proof by construction, which are my favorite, which is what this proof was in the beginning, before this version. And then we got with Greg and Denny, and we're like, we can turn this into a direct proof. And it is stronger because of that. The proof of construction, I'm going to get into a little bit. I'm going to show you some of the things that led to this proof. For a proof by construction, and I put a link to the video in one of the last videos. But let's just say it's it's kind of like the way I like to operate. If you go to my ResearchGate, you see I have a couple patents up there. I'm interested in inventing things that don't exist and making them from my imagination into something real. And so a proof by construction fits with that model, and that's exactly what I did. But then once you have that, if you can get it into direct proof, it just seems to be a lot more straightforward, right? So you don't need to go back and forth with a couple things. Very straightforward. All right, so let's get some definitions out of the way. All right, definition of property 1. We discussed them a little bit, but we got to revisit property 1. All right, we talked property 2, the mutually exclusive property. But property 1 is this. It is that if there are any non-trivial zeros off the critical line, non-trivial zeros of the Riemann zeta function, then they must exist at the vertices of rectangles symmetric across the real line and symmetric across the critical line, okay? And this mathematical identity sums that up. So if that is the case, there are imaginary parts of rho. Let's let rho be a non-trivial zero off the critical line. All right, critical line, we got the complex plane here, we got the real line, it's 0, 1/2, 1. We got pi out here a little bit, -2 over here, that's the real line. All the numbers you know and love. And the imaginary numbers are just multiplied by the square root of -1, which are, we would just call that I. So I times the imaginary, but here we got it, we get like Cartesian coordinates, okay? So the critical strip, as I was talking before, if you're not familiar with this, go back to the other videos if you can bear to watch them. But let's just sum it up again here, all right? So we have 0 here. There's a real number 0 and imaginary number here, zero here. All right, and this is where they'd have a real part. So if we take a point, let's say real part, let's say the S or rho equals, I don't know, 1/4 plus I7. Okay, so we kind of go over 1/4. I deliberately put this right in the middle so we can see. So that's 1/4, and then we count up to 7. It would be about here. And we plot a little point. So point here, point here, point here, point here. If there are, and this follows from Riemann's paper, if there are non-trivial zeros off the critical line, they're going to be at these vertices of rectangles symmetric across the real line and symmetric across the critical line. So you could say that that rectangle is internally tangent to a circle centered on the real point 1/2. You also could say that rho of h is the reflection of rho of 1 minus rho h. Let's just call this rho here. All right, I'm not going to say rho. No, let's say it because I'm going to deal with other rows. All right, rho h. Rho h is the reflection of 1 minus rho h through the point 1/2. Not the critical line, but the real point 1/2. So that's right there. So it's going to go, and if we take this line, stretch it up here, and this line, stretch it down here, it's still going to be going right through the 1/2. Okay. What it also means is that another way to sum up the Riemann symmetric vertices property is the way we're going to use it here, which is the imaginary parts of these guys are equal. This 1 minus the complex conjugate of rho h and rho h are going to share the same imaginary parts. This line, the distance from here to here, are going to be equal when the real parts of them sum to 1. So if we have 1/4, real part 1/4, and real part 3/4, 1/4 plus 3/4 equals 1. And if we move this off a little bit this way, if it's symmetric, this one's going to be this way, they're going to sum to 1. This is an identity, and this is going to be the case for all of them. The question is, do any of these exist? Okay, that's property 1. Definition of property 2, we went over a little bit. It's where upsilon equals 0 and zeta function equals 0, and upsilon does not. And the other property, or the other type of 0, is upsilon not equal to 0 and zeta equal 0. Oh my goodness, get a drink of water. So the big issue with this is looking at it from the functional equation here. We're going to call it oscillator equation. All right, because we're going to get into that. All right, so here's upsilon in the middle. You see him, where is he? There. Okay, if this equals 0, then this is going to go to 0. This is going to negate this, okay? Or you could say that A is equal to minus C omega squared. All right, so the big thing about this is that they're mutually exclusive, okay? You can't have one without the other. So upsilon, all right, we're going to take upsilon. We're going to let zeta equal 0. It just kind of drops off. And so we can express upsilon here for all of the zeta zeros. And where the first type is going to be A equals minus C omega squared when upsilon equals 0. See how that works? And the other type doesn't reduce any, but this is how we're going to identify it, by upsilon not equal to 0. All right, biggest thing to take away from this, they're mutually exclusive. You cannot have one be in one and then be in another. So that is the issue, the big issue with the Selberg Euler products, okay? They're both in this second type. There is none of the first type. They don't have any terms that go to 0, okay? They don't have any upsilon, right? You can't make an upsilon out of that, all right? You'll see by trying it. All right, and this is the thing. I don't need to prove, no one needs to prove the Selberg Euler products are not applicable to proof because there's an infinite number of them, all right? So all we do is we prove it with the zeta function here in this paper. And then if there's a counterargument, that burden of proof is on somebody else, all right? Because this is not a proof on Selberg Euler products, right? This is a proof on the zeta function, all right? So that's the catch. But I do sympathize with the situation because I do know that's going to be the first thing is you're going to want to apply Selberg and see how it holds up, okay? But I'm telling you, they don't have this linear type. They do have zeros on the critical line, but they all follow the same form. And then you have to make sure that they are not in one of the both. All right, they have to be separate. You will see why it's very important as we move forward. And then the theorem of the paper is simply the hypothesis proven. All right, the real part of the non-trivial zeros are equal 1/2. Okay, and we're going to do it with a direct proof. All right, so this is what I like to look at. And if you watch the other videos, you will have seen it before. How are we going to do it? We're going to take the functional equation. And first, I'm going to explain how I see things here. All right, this is how I saw things back, when I made the finding, and it came from a lot of work. I've been working on the Riemann hypothesis. I think when I made the first of these videos, it was probably the 17th year. Now we're in the 18th year. I've been working on it, but it's kind of like was proven a year ago. The paper's been out public for what, 6 months now, and 6 or more, and we're taking our time. You know, we want people to poke at it and hammer on it. We want it to be right, or we want it to be wrong. We want to know, and that's good. We don't care. We are seeking the truth. That is it. All right. So good. In fact, I miss working on it. You know, it was a great problem working on 17 years out of my life. So if there is something wrong with it, I'm very happy to get back into it. Okay, so this is an area of research that I'm very interested in. So if it's not done, great. I mean, my wife's probably tired of it, but I'm excited about that. I don't have a problem with it. But as I got into it, I didn't find any problems, and our co-authors don't find any problems. And out of the 5,000, close to 5,000 readers of it, no problems have been found. Okay, that's kind of significant since it's a very straightforward proof too. This is what I was looking at and what I was thinking. What if we could imagine like this film, this translucent film over the functional equation, and what if we start peeling it back and expose all of these rational properties underneath it by putting all of the irrational properties of the function equation, like pi and sine and gamma function, even zeta, and compact them right into a new function, upsilon. So we take out all the irrational properties and leave behind this rational skeleton of a relationship between some function, upsilon, and the zeta function. You see that? So basically we're just kind of peeling it away and leaving them behind the skeleton. And with that, then when the zeta function equals 0, upsilon is just a polynomial. The zeta function is never a polynomial, but when the zeta function equals 0, upsilon is a polynomial. Isn't that kind of cool? It is, actually. So what are these different functions underneath there? Well, the first one's Riemann's functional equation. The next, as we peel it back, is the Abel-Plana continuation of the zeta function. And the third one is the oscillator form that we use in the paper. All right, so why is it an oscillator? Well, we're going to get into it. All right, so here's the polynomial that's left over when zeta goes to 0. And what we're going to do before we get into the oscillator, I'm going to show all the things we're going to do in this proof. All right, we're going to show it really quick in a very simple way. I hope it's simple. We're looking at this situation, all right, this equality or inequality. We don't want this polynomial to be equal to 0, okay, when zeta is equal to 0. Why? Because when it's equal to 0, that means all the real parts are equal in half. So we're looking at all of the cases where this cannot be 0, all right? Can it be 0 when s equals 1? No, because it'd be undefined. Can it be 0 when s equals 0? No, because it'd be undefined. And that wouldn't even be a 0 of the zeta function anyway. But we're just going to look, because we don't know of any, non-trivial zeros off the critical line, so we have to just look at the cases of what we're doing. And we're going to cut them out, or we're going to set them aside. So with this expression right here, we have cut out all arguments of the zeta function that don't equal 0. These are all the zeros right here, trivial, non-trivial, all of them. Now we're just going to cut out all the rest. And we're just keep chipping away. So we did that. We're going to peel this back, look at it, evaluate it, cut out all of the possibilities of B0, and we're going to put it into 2 groups. Real part equals 1/2 is cut out. Okay? Why would that be the case? Even if you ignore the fact that this is 0, look, if we apply the real part 1/2 here, this is going to make this equals 0. All right, so it doesn't take much to see that the numerator is equal to, can be imply real part 1/2. But let's just see what we're doing. We're cutting out, eliminating all possible zeros, okay? And then we're going to eliminate, this is the part of the proof, we're going to eliminate the cases where zeta of 1 minus s are applicable. That would be the critical zeros off the critical line. So if 1 minus s, we have to eliminate them too. And that way we leave behind only the trivial zeros are applicable to this polynomial. Got that? Okay, good. So that is what we're looking at. This is our guy, all right? This contains all of the zeros of the zeta function, critical, non-trivial, and so on. All right, this then has 2 types. Real part of s equals 1/2, because the numerator implies, if it's real part 1/2, that implies 0. All right. And the other type, real part of s not equal 1/2. That's all we're doing. We're isolating in two different groups. And that can be explained in terms of upsilon. Upsilon equals 0 and upsilon not equal 0. Make sense? Why do I call this an oscillator? Well, it is actually. It's an oscillator in every way, shape, and form. I'm going to show you, though. It doesn't look like it currently. But let me just go show you. All right, look at the first term. I'll let drink water. First term, okay? So we're going to define that as a function over s. And you may be saying, well, why don't you have the s in parentheses like the zeta function? You'll see why. All right, because it actually is designed from a t. So when you have a function with a constant variable, you want to subscript it. When you have an overchanging variable like t, where it's kind of like an oscillator is taking over t, it's going to change with respect to t, but s is going to stay constant with that. And then you put the t in the parentheses. So zeta function here, we're going to change all this. We're going to show how it actually was originated as an oscillator, and it's pretty neat. All right, let's go. All right, so we don't have any calculus in the paper. All right, so you don't need to follow this, but understand that this can be done. Okay, so 1 over s minus 1, which is we defined as a as s, can be given by this. It's obviously the analytic continuation of a geometric series, and this this is the portion for whenever real part of s less than 1. I'm not going to get into it. I kind of discussed it in the last video, but the important thing is that when t equals 0, you're going to get 1 over s minus 1. Got it? But a of s is also the derivative of b of s. Well, what's b of s? It's the second term, okay? And in the same way, we defined that as b of s equals minus 1 over s minus 1 squared. And that also we get by integrating a sub s over t, right? So that's what I mean by having a derivative, okay? And at t equals 0, we get minus 1 over s minus 2 squared. Same thing in terms of b of s and c of s. All right, it's also the derivative of c of s. What's c of s? It's 1 over s minus 3 cubed in the third term. All right, this is how a harmonic oscillator works. Now watch this. All right, so and of course then if you integrate bs of t, then you get c of s. Okay, good. So you get that. All right. Now what is this other ugly identity here? I times the what is I times the complex conjugate of s. Well, it's very important, and I'm not going to get into too much, except that in terms of an oscillator would be called the fundamental frequency, which is often denoted omega naught. Okay, so we just kind of call it omega s in the paper, but let's continue by calling omega naught so you can see this in terms of a driven harmonic oscillator. In a oscillator or a driven harmonic oscillator, you're usually going to get the damping ratio, which is equivalent to upsilon. It's going to be denoted usually zeta. Well, since we're describing the function, zeta function, we don't want to double up too much, so we call it upsilon. All right, so too many zetas spoil the soup. All right, so we're going to call it upsilon, even though it functions exactly like a damping ratio, the damping ratio. All right, so what happens when you have a driven harmonic oscillator or any oscillator with this damping ratio equal to 1? It's a damped oscillator or a damped driven oscillator. Undamped driven oscillator. Now, I don't really know if these exist in nature, but since this happens mathematically, physicists, that would mean, perpetual motion type of thing. All right, so undamped means it's not slowing down. All right. So I don't know if they exist, but mathematically they do. All right, and engineers, physicists typically say, okay, well, if zeta in this case equal to 0, then it's an undamped oscillator. That's all we're going to call it. I don't know if it's a perpetual motion machine. I honestly don't. I think there's probably different descriptions of it. There is friction in all of these. Without friction, you wouldn't have force in the oscillator, but it's undamped, we would say. All right. Greg knows more about this. He says he can do these oscillator equations in his sleep. He studied Stanford on all this. I'm I'm familiar with them because one of my first inventions was an oscillator, a new type oscillator, and I guess some electrical engineers called it a feedback loop, but it is interesting. Anyway, so I know a lot about it, but not too familiar with undamped oscillators, except that upsilon, if it were that damped ratio, then it would equal to 0. Good. Okay, so if we showed how these are derivatives, so this is now starting to look more like the an oscillator form, all right? So in fact, that's exactly it. Now, why would we have it equal to zeta of s? Well, we got to look at it in terms of a driven oscillator, okay? So a driven oscillator, so if, let's say our oscillator is a swing, a person swinging back and forth, okay? So it is force, mass, and all of the physics along with it. F of t, and driven harmonic oscillator, would be some function over a constant. If this equation here is a swing, a person swinging, this would be a force of somebody pushing that swing, okay? So this oscillator has force, but this is an external force that is pushing that swing back and forth. And the constant in this case would be mass, okay? So an oscillator can be used in a variety of different applications. I mean, electrical coils, and that was my invention. So it doesn't need to be necessarily, you know, force, okay, can be, I don't know, voltage, anything. All right, so, but essentially, how does this apply to the zeta function? All right, so, I mean, we, in the paper, proved this, the zeta function takes this form. Okay, so, in this case, force, or F, would be analogous to the alternating zeta function over 1 minus 2 to the power of 1 minus s. So, the alternating zeta function is also called the Dirichlet eta function. So I kind of, and Jonathan's now, you'll see some acknowledgments in the paper at the end for him. He would call the alternating zeta function with to the power of an asterisk, but since I use that as complex conjugate a lot in my notes, I just call it, I denote it here. Okay, good. So then this is going to get really interesting. You're going to see something neat about the zeta function. It's a new form, a new series form of the zeta function and how it can be mapped geometrically. All right. All right, you get how this is starting to look like an oscillator. Well, oscillators, actually, it fully looks like an oscillator here. All right, oscillators are often graphed in phase space, okay, because phase space is identical to real space in some respect. If this is a spring, a weight on a spring going up and down in real space, then in phase space you can map it like more like a spoke on a wheel going around, and the distance would be could be measured as being equal. So you can see how, and there's some videos online where people kind of do this, and they have a wheel and they turn it and they show it looks just like something going straight up and down. Okay, not terribly important, but it is important in terms of graphing. Okay, when you graph this, and if you take this velocity and you make this the real line, and you take this position and you take this, make this the imaginary line, you can do some neat stuff, which I'm going to show here. All right, take the tangent half angle formula proof here. This is a proof without words. This is not my proof, and I apologize because I know this mathematician is still alive, and well, I hope he watches this, but I hope he doesn't watch it. I forgot his name again. The other video, I'll put it in the comments. But he was an editor of journal, and I'm drawing a blank on the name. I should take better notes for these. But this is all unscripted. You know, I'm just kind of I put some slides up and I talk about it. That's all this is. And I'll post his name in the comments. I'll go find it again. So he posted this, and it's a proof of the tangent half angle formula. Okay, so what is all that? All right, this one's on the real and imaginary lines. You can do it with Cartesian coordinates. All right, but so you have 0 down here, and you have the real line here, and imaginary here, and you have this angle phi, and you have then this u, which is the height from 0 to this line here, which is not labeled very well, but in his proof it is. And you get that the cosine of phi is equal to 1 minus u squared over 1 plus u squared, okay? So if you take the distance from here to u, from this point over here, and this is the unit circle, so the radius would be 1, then you would get the distance from this line to here as sine of phi, and this line equal to the distance cosine of phi. And that would be equal to 1 minus u squared plus over 1 plus u squared. So this is very, very neat. And I'm going to ask you, all right, for all of those that have worked on the Riemann hypothesis, a zeta function, anything, or anything to do with the zeros of the zeta function, tell me you haven't thought how this might apply to the zeta function. The tangent half angle substitution, tangent half angle formula. Tell me you don't see the temptation to see. I mean, the angle here is automatically 1/2 of the angle here, and this angle is. All right, there's got to be some way to tie in the zeta function if the Riemann hypothesis is correct. Okay, there is. This is where the proof comes from. This is why I'm sharing it. It's not in the paper, but I'm going to share it with you here. All right, and I discussed before this other version, this other form of the zeta function I had, and I said I wasn't going to get into it, wasn't going to prove how. I'm going to show you how to do it here. All right, if you integrate the right-hand side of this identity, all right, and add 1 and integrate it, you get pi, okay? Now we divide this by 2. We can divide it by 2, which doesn't change the way anything looks, or we can pull this 1 out like this. And you get a little bit of change of signs here, okay? But isn't that beautiful? And then you get pi divided by 2. Why is it interesting? Because then, watch this. You're going to like this. All right, so let's see. So you see the 1 minus u squared, all right? We just pulled out the 1, but it left over. We pull it out, and we get pi divided by 2. All right? All right, that's kind of a weird way of describing it, but watch what happens. And so there's a different way to do it, but this is the most interesting way to show. So we're just trying to pull that 1 out, and we put it in on purpose, and we're going to pull it out to divide by 2. Okay, it's very weird. All right, now watch this. You see the 2 here. All right, so we're talking about that tangent half angle formula, right? It was on the unit circle, so the radius is 1. That's where the 2 comes from. I will show you. All right, so we want to eliminate that 2 and call it S. Then you get this neat thing where phi becomes equal to the argument of S, okay? So you get that identity. When you do that, you get this equality, and where you can define u as the absolute value of the cotangent of 1/2 the argument, and phi becomes the argument of S. Now, we have turned that tangent half angle formula into an argument of S, and we get this zeta function out of it. This is the zeta function. It gives you all of the values of any other zeta function, of the zeta function, all right? And it's taken over u, which are, you can call it n if you want, but I want to show you where it came from. That was from the thing. Now, you may say, well, okay, but it's changing signs a little bit here. Yes, it does, because we got this oscillation right here. And you may say, well, that's not oscillation, it's switching. Yeah, it's switching if you're taking it over the natural numbers, or but if you take it over t, over any argument instead of just n, then we're no longer talking about the zeta function. We're talking about a zeta function, some argument like the zeta function over t. All right, but this is identical to the zeta function right here. This is identical. You should look up, and it's not even published. So that's cool. I'm publishing something for the first time, new form of zeta function on YouTube. Isn't that neat? But you're going to like that one. All right, let's look at this identity. All right, so this is easier, and we're not talking about the natural numbers. All right, we want to talk about it over t, over rational arguments, t. Better to use it as cosines and parametric equations, okay? And then you can start to do neat things with the tangent half angle formula like this. Now, if we consider this an oscillator over arguments t, and of course, there is no t in this equation, okay? So we should drop that out. But if we take it, particularly, remember it's an oscillator, it's in the oscillator form, namely the, somebody use the microwave here, the alternating zeta function, okay? Alternating zeta function. And we can take this over t, and I want you to see how it all lines up on the tangent half angle formula. The generalized tangent half angle formula. Obviously, if this is S, this point, remember the angle is argument S, this point is S. As we stretch this and change this, the radius of the circle is going to change, because we don't want it dependent on we don't want the unit circle anymore. We want it to be given by S. U is still there. Some of the properties are going to change a little bit, because it's not unit circle anymore, but we still get the value u meaning something, right? But the most important thing is that the zeta function fits in there, namely the alternating zeta function. It forms the spiral. Now it's locked in there. All right, so if you take this, the inverse of the imaginary part of S, that's the radius to this circle. This yes, it's marked 1 right there. So the distance here is 1. That's always going to be 1. And then you get this circle tangent to it. The inverse imaginary part of S is going to line up with, have this property. The initial angle tangent to this spiral formed by the alternating zeta function over t is going to have this constant right here, 1/2 times pi divided by 2 minus argument of S. Now the angle changing as t changes. Now if we let t be integers, then it becomes more familiar like the zeta function. But if we just consider any t as it goes around, this is the equation that governs the distance of the tangent angle to the angle of perpendicular to the radius. All right? Now what's really interesting here is that the distance to the spiral, the tangent angle, the distance from 0 to the tangent, oh my goodness, to the line tangent to the, oh my gosh, what is that term? I'm drawing blank. Well, I practiced this earlier and my brain's going downhill fast. Okay, but look at that line right there. Is t to the power of minus real part of S, all right? It is governed by that. And the radius of where the spiral begins is governed by the imaginary part, okay? So this is kind of neat, you know, I think. And maybe not. You know, Greg and some others, it's very complicated, you know, so I didn't put it in the paper, but this gives me all the information I need to do to find all the geometry of the zeta function, because yeah, zeta function not on here, the alternating zeta function is, and it's all the points on here. So if you take, let t be the natural arguments, and you take its point here, which I don't know what is, minus, I don't know, something, you know, this would be minus 1 plus something, depending on the argument, and then you're going to get, so that at t equal, let t be n, okay, the natural numbers. All right, so the first one's going to be in here, and you may get 2, argument 2 over here, and it's going to flip over here, and it's going to be flip over here for all the integers. And then you sum all those up, and that gives you the normal alternating zeta function. And it's actually not the alternating zeta function specifically, it's the minus complex conjugate of the alternating zeta function, of which you can get the normal zeta function out of, okay? So that one actually fits nicely because that is the external force of the oscillator. Okay, so what about the terms? Now this is the oscillator form of the, explicit form of the oscillator form of the zeta function, and which is used in the paper. None of this is in the paper, all right? Just this equation alone is, all right? And upsilon. But studying this will help you to understand, you know, the gold behind this proof, okay? It really is in the physics that build up to it, all right? So yes, it's simple. The algebraic proof is simple. It was not conceived in a simple way. It was it's pretty sophisticated. Now here, 1 over s minus 1. Does every part of the zeta function lock into the tangent half angle formula, the generalization of it? Yes, it does. 1 over s minus 1, where does that lock in? Now remember that 1 over s minus 1 is equal to this function, which the u's, right, which we had before, but it's also, if you remember, if we sum this, we're getting the normal zeta function. 1 over n to the power of s over the integers summed is going to equal the zeta function. When you integrate it from 1 to infinity, it gives you the geometric series, this value here. All right, so where does that fit in on the tangent half angle formula? Okay, so same line, same circle, 1 over the imaginary part of s. Okay, now we take the plane section of a double-sided cone internally tangent to that circle, and then take another circle internally tangent to the base of the plane section of a double-sided cone, and that point right there. That right there, mathematically, that's where it lies. So you can use all the different geometry to link in this value here to the zeta function, or particularly the minus complex conjugate of the alternating zeta function. Geometrically, it has that relationship to it. Yeah, you didn't know that can be done, did you? And you can do the same thing with 1 over s minus 1 squared, and 1 over s minus, and I had the map, they form all the points. It gets really cluttered fast, that's why I just do one at a time. But that's locked in there as well, okay? So there's no degrees of freedom in this, between this relationship and this. We change s, everything changes with it. You see that? But that is 1 over s minus 1 geometrically. Proof without words right there. All right, cool. Now let's get back to the proof. All right, so that's what That's the oscillator. That's why I call it oscillator form. Now, here's how the proof is going to go. All right, lemma 1. We just need to show that zeta fits in that form. That's all. We just need to derive it from the functional equation of zeta. We can derive it from any. The original derivation was from the Abel-Plana derivation. And so, but then we were like, well, we don't want to have an analytic complex analysis proof. We want it to be algebraic, so we're going to use a functional equation. Then everyone cries, oh, but the other oil products, the Selberg oil products are, no, it's not an analytic, proof. It's not a, we're not talking complex analysis here. We're talking about complex arithmetic and algebra, all right? So we can do it right from here. We don't need to do any calculus. We derive it straight from the functional equation, and in this case, we would not allow s to equal 1. Okay, so we eliminate that with lemma 1. All right, now then we get lemma 2. It's going to leave us just two types of zeros, when upsilon equals s and upsilon of s not equal to 0. Good. Okay, so that's going to come from this form. All right, here it is. All right, a of s. And we've been over this, right? You see them all? Omega s. All right, so this happens on page 5. Okay, we finally get the identity of upsilon on page 5, equation 2. All right, there's other equations in between, but that's the first one we numbered. It's significant. Outside of the paper, if you want to know more about upsilon, pause this and write this down right here. Here you can get, for any argument s except for 0 and 1, because they're undefined, you're going to get an output for upsilon. All right, this integral converges even for 0 and 1, but of course this multiplier does not, and this term does not. Okay, see, because yeah. All right, this one works for s minus 1, but not s equals 0. But you got to use them all, right? So, but this is a very useful function. So you want any value argue. Well, I want to plug in. I don't want to deal with zeta function. I just want to plug in arguments s to upsilon. Right here it is. Okay. If you want to see relationships between upsilon and zeta, use this one. Okay, just a little helpful. The first one, we didn't want any calculus in the paper, so this one is not in the paper. Doesn't need to be. We derive it in a different way. Good. All right, keep thumping on the keyboard. Sorry. I'll one day I'll have a studio and you'll never even hear it. Okay, good. Lemma 1 is completed on between pages 4 and 6, and there's our final result. It's in that form, and so the derivation is going up starts on page 4 and ends on page 6. Not too complicated, but it is fascinating. So definitely we might want to check it out. Okay, good. All right, lemma 2 is super simple. All we're doing is we're showing that none of those functions in zeta function can equal 0. None of them except upsilon. Okay, and it's very easy, because we went over them. They're reciprocals of s minus 1 to some power, and the whole proof is right here in a couple sentences. Okay, it says it explains why omega can't equal 0 and why the other terms can't equal 0. Super simple stuff. The reason is because 0 has no reciprocal, so very simple. All right, but it's a step that's necessary. We did say we're going to prove it. All right, good. Lemma 3 is a little bit more involved, but nothing you can't handle. Okay, so this is where the mutually exclusive property is proven. Okay, actually with the Selberg products, you're probably not going to get past this lemma 1. Okay, all right. Lemma 3 is where you actually can do something with them. We have to show we actually get the solutions. We get the solutions in terms of the real parts. All right, when upsilon is equal to 0 or upsilon is not equal to 0. Okay, and so we're going to do that in order to eliminate the critical zeros to show that they're not in the type 2. Okay, so again, this is the type 1. Upsilon equals 0 if and only if real part equals 1/2. That's right in the paper. We prove it very simple, straightforward. Upsilon not equal to 0 has to be real part of s not equal to 1/2. Wait, upsilon of s not equal to 0 implies, reverse implies real part of s not equal to 1/2. And remember, you can't have one in there and then a solution in this one as well. These are mutually exclusive. If they're in here, it's like a basket A and basket B. They can't go back and forth between the two, okay? And they don't. And it's very easy to prove. Okay, so that proof happens of lemma 3 happens on pages 7 and 8. All right, it's like a page and a half or so. Okay, and this is how you basically prove. You just basically take that form, express it explicitly, and the numerator also equals this, and 2 times real part of s minus 1 implies real part, if it's equal to 0, implies real part 1/2 because this cannot go to 0. It's pretty straightforward. Good. The second one, the type 2 solution in terms of the real part, is this one. And this is one people go, okay, how'd you get that? All right, so you can do the math yourself, and you're going to get a variety of different ways. But this is a form. It's very straightforward to get. All right, we reduced it. All right, so now we get this form. All right, so I wouldn't say we. Somebody gave it to us as a gift, and they were trying to disprove the paper, so it's one of those funny gifts. But what happened is, what he's doing is he took the this factor out of the square root, and the sign's reversed. So the positive solution to this corresponds to the negative of this when you do that. But that's okay, because for any argument you put in here, you're going to get the same value out. And what it does is something super beautiful. This, I mean, admittedly, this is a lot simpler to look at, right? A lot easier to prove the final result too, and this lemma as well. Because look, looking into we call this reduction of equation 7. All right, and this happens on page 7 and 8. All right, look at this second term here on the right. All right. Does that look like it has any values in the real? No, it doesn't. It is not, it has 0 elements in the real. You can't get that I out of there, no matter what you do and pull and twist. It's not, and that can be proven easy. It's actually pretty straightforward. All right, but most important thing is the way it applies to here, because that has to go to 0 if you're going to get real part equal to 1/2. You see, because you pulled the 1/2 out there, it's out there. So this has to go to 0 if you're going to have any solutions real part equals 1/2 in the type 2 solution. So isn't that neat how he did that? And I said, oh, dude, I'm stealing that. I'm sorry. He didn't write it. And I want to give him acknowledgments, but he didn't want to be acknowledged in it. So I'm like, okay, well, we're still using it. It's just a reduction of it. And I like it. It makes it very easy. Now watch this. Watch this. Okay. Oh, yeah. So then here we have the proof of the theorem, which comes down to, we're just going to ask the question, is that even mathematically possible with that type 2 solution? Is it mathematically possible to have any symmetric solutions across the critical line from each other? All right, and it's very easy to show that you can get some with well, we could do the real line, or we could do the critical. We're doing the across the critical line. Okay, that's where the whole proof is. And we do that by summing it, applying the real part solution, which is here, the reduction of 7. We're going to apply that to the identity which I discussed before, where the identity of rho must sum to 1. All right. So, and the proof of the theorem shows that there are no solutions. There's none that equal to 1 when those imaginary parts are equal to each other. And that's done right here on pages 8 and 9. If you take them, this is some of this has been revised. Okay, it's simplified because we have this reduction in there now. So if you've read the paper before, go check it out. So now we just kind of pull out this 2 times imaginary part plus I. We pull that out of the parentheses, and what we left with, a simple. Only possibility of any solutions off the critical line must occur when upsilon of rho h equals plus or minus upsilon of 1 minus the complex conjugate of rho h. Why? Because those square roots are going to be equal. If you take the explicit form of 6 and 7, you apply this, they're going to be equal for any time you do this. All right? See this? These square roots there, here and there, they're equal whenever, for any arguments, 1 minus complex conjugate of rho. All right? That's kind of just, everything drops out except this, so we only have 2 things to check. Now watch this. Well, it can't be equal to the positive because that's only possible for real part equals 1/2. So if you show them in an explicit form, they're going to reduce, just going to reduce to 1/2. And that is the case for all of the vertices. So that means that if you have those 4 vertices, if they were possible solutions off the critical line, upsilon is not going to be shared by any of them. All right, so upsilon, we already know upsilon is not going to be 0, but this means that all of upsilon, none of those 4 upsilons corresponding are going to be equal. The only other possibility is when upsilon equals upsilon minus upsilon. But what happens when we apply that to the reduction? This here, let's just plug it in. If this is equal to upsilon minus upsilon, ignore the 2 there, minus upsilon times 1 minus complex conjugate of rho, all right, is equal to upsilon, and the square roots are equal to each other, everything reduces to simply upsilon equals upsilon. Now think about that. That's just an identity. That's not a solution. We can even go further. If it was a solution, which it's not, if upsilon was equal to upsilon, if that meant anything at all, which it doesn't, that would mean that that rho equals rho, and the real part equals real part, and if the real part equals the real part, add them to 1, that means real part equals 1/2. But it doesn't mean that, because it's not a solution. It's nonsense. It's just an identity. All right. So this is the way it's summed up. All right. So you can't have any. If you can't have the complex conjugate of this, then you can't have this guy here. All right. It's impossible. There are no critical zeros, symmetric critical zeros in the type 2 planar solution. All right. Well, the proof then comes down to everything we've already done. All right. Let's take a look. All right. The negative solution for 7 is extraneous. Okay. It doesn't work. It has no solution. There are solutions for the positive, which we'll get into. Okay. The set of all, and we were saying when you have this identity, it means this: the set of all output values that upsilon 1 minus rho h could produce is empty. Okay. So if you have a function, then it has to output an image. So if you take a picture of the camera and it doesn't output anything, you don't get a solution. All right. That's the way you look at it. You say that the entire image is gone. There's no image there. Okay. So that means there's nothing in it. There's no critically symmetric non-trivial zeros in the type 2 planar solution. All right. So the type 2 does not comply with property 1. All right. Therefore, it contains only trivial zeros. So -2, -4, all those work. Okay. So there's what we want to show. That one works. All right. The trivial zeros fit in there. All right. But there are only 2 types of solutions for zeta equals 0. And that was all, as you saw, if you just drop out whenever zeta 0, there's only 2 types of solutions. And we just showed that there's none that are critical or that are critically symmetric. And the first type is all real part 1/2. There's only 2 types. So all the non-trivial zeros of the Riemann zeta function are type 1, but those all are real part 1/2. What does that mean? The Riemann hypothesis is correct. And I thank you for your time. My name is Jeff Cook. Hope to see you in the next one, and hopefully be doing something other than this proof. Please do feel free to ask questions. I am leaving space in my mind to make another video on this if something significant comes up. But good luck, and please use both sides of your brain. Have a good night.